It's super dramatic to be under this bridge. It's beautiful, and it is remarkable how high this bridge is and how long it extends.
What China just built 78 meters under the ocean is absolutely terrifying, and nobody's talking about it. While America was distracted, they pulled off the impossible. 2 apartment-sized machines tunneling through solid rock from opposite directions met with only 2 centimeters of error. Pentagon insiders are calling it a game changer. This isn't about trains or connecting islands. This is about something far bigger, and the implications will shock you. What they're planning next could reshape global power forever. Picture this scenario for a moment. You're traveling on a train moving at 250 kilometers per hour. That's fast enough to overtake most vehicles on a motorway. But here's what makes it extraordinary. You're not racing across open countryside or through mountain valleys. You're 78 meters below the ocean floor. To give you some perspective, that's roughly equivalent to the height of a 25-story building, except you're that distance beneath the seabed instead of above ground. While you're down there, massive cargo ships are passing overhead through one of the planet's busiest shipping corridors. The water pressure at this depth is immense, powerful enough to crumple a vehicle like it's made of paper. Yet passengers on this train would be traveling in normal comfort, perhaps checking their phones or having a meal, completely insulated from the extreme environment surrounding them. This isn't a concept from a science fiction film, it's a real project currently under construction in China. The country is building an undersea railway tunnel that, when completed in 2028, will break multiple records for underwater rail infrastructure. We're discussing the Gintang Undersea Tunnel, a structure that stretches over 16 kilometers in total length, with more than 11 kilometers of that distance running directly beneath the seabed. To understand the scale we're dealing with, consider that 11 kilometers is farther than many people commute to work each day. The difference is that this particular route involves 2 enormous tunnel boring machines, each comparable in size to an apartment building, excavating toward each other from opposite directions deep underground. And they need to meet with the kind of accuracy you'd expect from precision surgery, not heavy construction equipment. The engineering challenges involved have led some experts to question whether such a project was even feasible. Yet China is not only attempting it, but doing so at speeds and on a scale that makes other countries' underwater tunnel projects look modest by comparison. But before we examine the technical details of how they're accomplishing this, it's worth asking a more fundamental question. Why build such a tunnel in the first place? The answer lies in geography and connectivity. Zhoushan is a group of islands located off the eastern coast of China. It's a region known for its fishing industry, coastal scenery, and notably one of the country's largest offshore petrochemical facilities. Despite its economic importance, Zhoushan has lacked direct rail access. If you wanted to travel there from the mainland, your options were limited to taking a ferry or driving across a series of bridges. While these methods work, they're not particularly efficient when you're trying to move large numbers of people and substantial amounts of cargo quickly and reliably. China's solution to this problem was to construct a high-speed rail line that runs beneath the ocean. At this point, you might wonder why they didn't simply build another bridge. After all, China has plenty of experience with impressive bridge construction. The answer comes down to several practical factors. Bridges occupy surface space and can interfere with shipping routes, which is a significant concern in busy maritime areas. In locations where the water is particularly deep or subject to severe weather conditions, bridges become impractical or prohibitively expensive. Tunnels offer a solution that sidesteps these issues entirely. They're unaffected by surface conditions like storms or waves, and ships can pass overhead without any disruption. This tunnel is part of China's broader infrastructure expansion. Over the past 10 years or so, the country has constructed approximately 45,000 kilometers of high-speed rail track. That's more than all other countries combined during the same period. They've gained extensive experience with bridges, elevated structures, and mountain tunnels. An underwater tunnel of this magnitude represents the next frontier, a challenge they've decided to tackle head-on. The Gintang Tunnel isn't just any underwater passage. It's specifically engineered for high-speed trains traveling at 250 kilometers per hour. That velocity exceeds what most cars achieve on highways, and this is happening 78 meters below sea level, in an area with some of the most complex geological conditions imaginable. The seabed in this region isn't uniform. It's a mixture of different rock types and soil compositions, each presenting its own set of challenges for tunnel construction. So how do you actually begin constructing something of this nature? The answer involves some truly impressive machinery. The project relies on tunnel boring machines, often abbreviated as TBMs, but these aren't ordinary construction vehicles. They're specialized pieces of equipment built specifically for the extreme demands of underground excavation at this scale. The two machines deployed for the Gintang Tunnel have been given names, Dingai and Yongzhou. Each machine measures roughly 150 meters in length. To put that in context, that's about half the length of the Eiffel Tower if you laid it on its side. The cutter head, which is the large rotating disc at the front that actually cuts through the earth, has a diameter of nearly 15 meters. Imagine a circular saw blade as wide as a 5-story building is tall, spinning with enough force to slice through solid rock. These machines each weigh around 4,000 tons. That's approximately equivalent to 8 fully loaded Boeing 747 aircraft. But their size is only part of what makes them remarkable. They're highly automated engineering systems. As the cutter head advances and excavates material, the machine simultaneously removes the debris, installs reinforced concrete segments to support the tunnel walls, and injects grout to seal everything securely. It's essentially constructing a horizontal structure underground in real time as it moves forward. The geological challenges these machines face are particularly demanding. The term engineers use is mixed geology, which refers to the fact that the ground composition isn't consistent along the tunnel route. At one point, the machine might be cutting through hard granite, which is stable and predictable. A short distance later, it could encounter soft clay or sandy soil that can shift or collapse if not handled correctly. According to project reports, the machines encounter 28 different geological transitions along the tunnel route. That means 28 separate occasions where they need to adjust their operating parameters, including speed, pressure, and cutting technique, to prevent problems. To handle these varying conditions, Chinese engineers made specific modifications to the machines. They added water injection systems to the cutter head to deal with clay that might otherwise stick to and clog the cutting blades. They reinforced the sealing systems to withstand the enormous water pressure that exists 78 meters below sea level. They also upgraded the drive systems to ensure the machines could operate continuously for months without mechanical failures. Now, here's where the project gets particularly interesting from an engineering standpoint. These aren't two machines working independently. They're working together as part of a coordinated system. Yongzhou starts excavating from the Ningbo side, which is on the mainland. It digs forward for nearly 5,000 meters. Meanwhile, Dingai begins from the Zhoushan side, the island location, and excavates more than 6,000 meters. Somewhere in the middle, deep beneath the ocean floor, these two machines are supposed to meet, but they can't just approximate the meeting point and hope it works out. If these machines miss each other by even a few meters, the result isn't a functional tunnel. Instead, you end up with two separate holes that don't connect, effectively making the entire project a failure. At that point, you've invested several years of work and spent billions of dollars without achieving the objective. The financial and practical stakes of getting this connection right are enormous. This brings us to perhaps the most technically challenging aspect of the entire project. Ensuring these two massive machines approaching each other from opposite directions through solid rock deep underground can meet with the kind of precision normally associated with much smaller scale work. That level of accuracy doesn't happen by accident. It requires sophisticated technology and careful planning at every stage of the excavation process. Consider trying to thread a needle. Now imagine that needle has an opening 15 meters wide. It's buried 78 meters beneath the ocean floor, and you're attempting to guide it from more than 6 kilometers away. If you miss, you've wasted years of effort and an amount of money that could fund a significant portion of a small nation's infrastructure budget. This is essentially the challenge China faced with the Gintang Tunnel project. The core issue here is precision. When you're excavating a tunnel from two different starting points, even the smallest error in angle or alignment gets magnified over distance. If your Harvard's initial trajectory is off by just 1 degree at the starting point, by the time you've traveled several kilometers, you could be dozens of meters away from where you need to be. And when you're working underwater, you can't simply stop the operation, take measurements with conventional tools, and make corrections. The environment is too hostile and the scale is too large for traditional surveying methods. So how did Chinese engineers solve this problem? The answer involves satellite technology, specifically a system called Beidou. This is China's satellite navigation network, essentially their version of the American GPS system. Beidou provides positioning data through a constellation of satellites orbiting the Earth. However, standard satellite positioning systems, while useful for everyday applications like driving or hiking, typically have an accuracy range of several meters. That level of precision works fine if you're trying to find your way to a restaurant, but it's completely inadequate when you need to connect two tunnel boring machines underground with almost no margin for error. Chinese engineers recognized this limitation and developed a more sophisticated approach. For the Gintang Tunnel project, they deployed 6 Beidou satellites dedicated specifically to this construction effort. These satellites were linked directly to the automated navigation systems installed on both tunnel boring machines. The systems continuously monitor the machines' positions in 3-dimensional space, tracking their latitude, longitude, and depth below the surface. The way this works is quite remarkable. As the machines advance through the rock, they constantly communicate with the satellites overhead. Every few meters of progress, the machines send signals to the satellite network. The satellites calculate the exact position of each machine, compare that position to the planned route that was mapped out before construction began, and then send correction data back to the machines. If a machine is drifting even slightly off course, perhaps by a centimeter or two, the system makes micro adjustments to the cutter head angle and the machine's steering to bring it back into alignment. Think of it as having a navigation system that's accurate to within 2 centimeters, providing real-time guidance to a machine that weighs 4,000 tons and is cutting through solid rock deep underground. The technology represents a significant advancement over what was available even a decade ago. According to engineering reports, this level of precision navigation was one of the key innovations that made the project feasible, and the system worked. When Dingkai and Yongzhou finally met deep beneath the seabed, the alignment error was measured at less than 2 centimeters. 2 centimeters on a tunnel exceeding 11 kilometers in length. To give you a sense of how extraordinary that is, imagine throwing a dart at a target from across a football field and hitting within 2 centimeters of the center. That's roughly the equivalent level of accuracy we're discussing here, except instead of a dart, we're talking about guiding massive boring machines through varying geological conditions underground. The successful connection of these 2 machines represents a significant achievement in tunneling engineering. It demonstrates that with the right technology and planning, it's possible to execute large-scale underground construction with a level of precision that would have seemed impossible not long ago. But this success creates another challenge, one that might not be immediately obvious. What do you do with these massive machines once they've met in the middle of the tunnel? This is a genuine problem in tunnel boring operations. The machines can't simply continue excavating forward because there's nowhere for them to go. They've reached their destination, and they certainly can't reverse back through the tunnel they just created. These machines are designed to move in one direction, pushing forward as they dig. The concept of backing up several kilometers through a completed tunnel isn't really feasible, even if you wanted to attempt it. Additionally, these machines are far too large to be lifted back to the surface from their current position. Each one weighs thousands of tons and is buried deep underground. Attempting to excavate vertical shafts large enough to extract them would be enormously expensive and time-consuming, potentially costing more than the machines themselves are worth. So engineers are left with what seems like an unusual situation: 2 extremely valuable and sophisticated pieces of equipment that are permanently stuck in the middle of a tunnel. The solution Chinese engineers employ is called shedding the shell, and it's exactly what the name suggests. The machines are carefully dismantled from the inside, piece by piece. Workers remove all the valuable and reusable components: the drive systems that power the machine, the cutter heads that do the actual excavating, the hydraulic systems, the electrical components, and the control systems. All of these parts are transported back through the tunnel to the surface. It's similar to gutting a building from the interior until only the outer structure remains. But here's the clever aspect of this approach. The outer steel casing, which is the large cylindrical shell that housed all the machinery, remains in place permanently. Rather than being wasted, this casing becomes part of the tunnel's permanent structure. It provides additional reinforcement to the tunnel walls and contributes to the overall structural integrity of the passage. In a sense, the machines don't just build the tunnel, they become part of it. Their final contribution is to serve as permanent structural elements, ensuring the tunnel remains stable for decades to come. From a practical standpoint, this approach makes considerable sense. The cost and effort required to extract these machines would likely exceed the cost of simply manufacturing new ones for the next project. The reusable components, which represent most of the machine's value, are recovered, and the remaining structure serves a useful purpose rather than being abandoned waste. It's an efficient solution to what could otherwise be a complicated problem. According to the latest project updates, the Gintang Tunnel is on schedule to be completely bored by the end of 2026. That's when the two machines will have completed their excavation work and met in the middle. However, boring the tunnel is only one phase of the construction process. After the excavation is complete, there's still substantial work to be done. The following phase involves what's known as fit-out work. This is when the raw tunnel gets transformed into a functioning piece of infrastructure. Workers need to lay the railway tracks along the entire length of the tunnel. They install electrical systems to power the trains and provide lighting throughout the passage. Safety equipment needs to be installed, including emergency exits, fire suppression systems, and communication networks. Ventilation systems are essential to maintain air quality and regulate temperature. All of these elements require careful installation and testing before the tunnel can safely carry passengers. This finishing work typically takes about a year to complete for a project of this scale. If everything proceeds according to the current timeline, the tunnel should be fully operational by 2028. At that point, the impact on regional travel will be significant. Passengers will be able to travel from Ningbo to Zhoushan in approximately 30 minutes. That's a journey that previously required over an hour by ferry or car, depending on conditions. The travel time gets reduced to less than what it takes to watch a typical television program, and passengers will make that journey in air-conditioned comfort, traveling at 250 kilometers per hour, 78 meters below the ocean, likely without giving much thought to the extraordinary engineering that makes it possible. But the Gintang Tunnel's significance extends beyond simply connecting these two locations. The project represents something larger, a demonstration of capability that has implications well beyond this particular stretch of coastline. The techniques developed, the technology deployed, and the expertise gained from this project don't just disappear once the tunnel opens. They become part of China's engineering knowledge base, ready to be applied to future projects. And according to many observers in the engineering community, there may be a much more ambitious project on the horizon. The Gintang Undersea Tunnel is impressive when considered on its own merits. However, many engineers and infrastructure analysts believe there's a larger story here. They suggest this project may actually be a test run for something far more ambitious: a tunnel across the Taiwan Strait. If you look at a map of the region, the Taiwan Strait is the body of water that separates mainland China from Taiwan. At its narrowest point, the strait measures approximately 130 kilometers across. That's roughly 8 times the length of the Gintang Tunnel. The water in the Taiwan Strait is deeper than what the Gintang project deals with. The ocean currents there are stronger and more unpredictable. The geological conditions beneath the seabed are even more varied and complex. Without question, such a project would represent the most ambitious tunnel construction in human history. But here's an important point about how major engineering projects typically develop. When you're planning to attempt something truly extraordinary, something that pushes the boundaries of what's currently possible, you don't just start building and hope everything works out. That's not how engineering advances. Instead, you practice. You build smaller versions of the project. You test your technology in real-world conditions. You refine your techniques based on what you learn. You identify problems when the stakes are lower and develop solutions before attempting the ultimate challenge. From this perspective, the Gintang Tunnel makes perfect sense as a testing ground. It allows Chinese engineers to demonstrate that they can construct a high-speed rail tunnel beneath the ocean at significant depths, maintain structural integrity under extreme water pressure, achieve precision measured in centimeters over distances of many kilometers, and complete the work faster and more cost-effectively than similar projects elsewhere. If they can accomplish all of this successfully with the Gintang Tunnel, it provides strong evidence that a Taiwan Strait tunnel, while far more challenging, falls within the realm of possibility. Whether the Taiwan Strait tunnel actually gets built is a separate question entirely. That decision involves numerous factors beyond pure engineering capability. There are political considerations given the complex relationship between mainland China and Taiwan. There are economic questions about whether such a massive investment makes financial sense. There are environmental assessments to consider, and there are logistical challenges about how such a project would be managed and funded. These are discussions that will likely continue for years, possibly decades. However, from a strictly technical standpoint, China has now demonstrated the fundamental capability. They've developed the machinery needed for this type of construction. They've created the navigation and guidance systems that provide the necessary precision. They've refined the construction techniques for dealing with varied underwater geology. And perhaps most importantly, they've built up the institutional expertise and experience base required to manage projects of this complexity. That's significant because for a long time, underwater tunnels were considered one of the final frontiers of civil engineering. Underwater tunnel construction is expensive by nature. The specialized equipment required, the time involved, and the technical challenges all contribute to enormous costs. These projects are also inherently dangerous, with workers operating in environments where mistakes can have catastrophic consequences. And they're technically demanding, requiring expertise in multiple engineering disciplines, working together seamlessly. For these reasons, most countries have built perhaps one or two major underwater tunnels in their entire history. Each one is treated as a unique, once-in-a-generation achievement. China appears to be taking a different approach. They're treating underwater tunnels not as rare exceptions, but as another type of infrastructure that can be deployed relatively routinely when needed. Consider the Hong Kong-Zhuhai-Macau Bridge, which includes an underwater tunnel section nearly 7 kilometers long. That project was completed in 2018. The Gintang Tunnel will be finished in 2028. And according to reports from Chinese infrastructure planning agencies, there are already additional underwater tunnel projects in various stages of planning and approval. China isn't just building individual pieces of infrastructure, they're developing a systematic approach, a repeatable methodology for tackling these challenges. They're creating what might be called a playbook for accomplishing things that most countries consider exceptional. This has broader implications beyond China's borders. Large infrastructure projects like this don't just change geography by connecting places that were previously difficult to reach. They also change perceptions about what's achievable. 50 years ago, the concept of a high-speed train traveling at 300 kilometers per hour through a tunnel 78 meters below the ocean would have seemed like pure fantasy, something you might read about in a science fiction novel. 20 years ago, engineers could theoretically describe how such a project might be possible, but the practical and economic challenges would have made it seem unrealistic for actual implementation. Today, China is building it, and they're already planning the next one before this one is even completed. That shift in perspective matters because engineering advances often happen through demonstration rather than just theory. When one country shows that something can be done and done efficiently, other countries pay attention. Projects that were previously dismissed as too risky or too expensive get reconsidered. Techniques that seemed experimental have become accepted as standard practice. The entire field of engineering takes a step forward. However, it's important to acknowledge that projects of this scale come with legitimate concerns and costs. Environmental impacts are real and need to be carefully considered. Drilling through the seabed disturbs marine ecosystems. The construction process can affect water quality and habitat. Long-term effects on local marine life aren't always fully understood at the time construction begins, and monitoring needs to continue for years after completion. Environmental impact assessments are part of the planning process, but there are ongoing debates about whether these assessments adequately account for all potential consequences. There are also social impacts to consider. Large infrastructure projects frequently involve land acquisition, which can mean relocating communities or businesses. The balance between infrastructure development and its effects on people's lives is complicated and doesn't always have clear answers. Projects that bring significant economic benefits to a region may also create disruption for specific communities, and finding fair solutions to these conflicts requires careful attention. The economic dimension presents its own set of questions. The Gintang Tunnel alone represents an investment of billions of dollars. That's an amount of money that most countries simply couldn't commit to a single infrastructure project, even if they wanted to. China is able to fund these projects because of its centralized planning system and its policy of investing heavily in infrastructure as a driver of economic growth. The government can direct resources toward long-term projects without needing to justify immediate returns. Whether this model is sustainable over the long term is something economists continue to debate. Some argue that this level of infrastructure investment creates genuine economic value by improving connectivity and enabling growth. Others suggest that not all infrastructure spending generates sufficient economic returns and that at some point the costs may outweigh the benefits. These are complex economic questions without simple answers, and different experts reach different conclusions based on their analysis. But regardless of debates about methods, costs, or sustainability, one thing appears undeniable. China is currently rewriting expectations about what large-scale infrastructure can look like. They're building faster than other countries, on a bigger scale and with greater ambition. Projects like the Gintang Undersea Tunnel aren't isolated achievements. They're part of a broader pattern of infrastructure development that's been continuing for years and shows no signs of slowing down. This raises interesting questions about the future. What happens when tunnels beneath oceans become routine rather than exceptional? When connecting islands, crossing straits, and linking continents becomes just another item on an infrastructure to-do list rather than a once-in-a-generation achievement? We're beginning to find out. The techniques being developed for these projects will likely influence infrastructure planning globally. Other countries will study what China has accomplished, learn from both the successes and the challenges, and apply those lessons to their own future projects. The Gintang Tunnel, then, represents more than just a connection between Ningbo and Zhoushan. It's a demonstration of how far tunnel engineering has advanced and a preview of what might be coming next. Whether that leads to even more ambitious projects like a Taiwan Strait Tunnel or inspires similar developments in other parts of the world remains to be seen. But the fundamental capability has been demonstrated, and that changes what engineers and planners around the world will consider possible going forward. So if you could design an undersea tunnel connecting any two places in the world, where would you choose? What regions would benefit most from that kind of direct connection? These aren't just hypothetical questions anymore, they're becoming practical engineering considerations. And the answers might shape how our world develops over the coming decades.